In the early days of physics, Galileo noticed, and have essentially experimentally verified, something kind of strange. Anything that you drop seems to fall with a constant acceleration. Not only a constant acceleration, but with the same constant acceleration no matter how big it is, no matter how heavy it is. All objects near the surface of the Earth seem to accelerate downward with the same magnitude acceleration. That's illustrated over here by a picture from a textbook where we have dropped an apple and a feather into what is probably a vacuum chamber. And there's a constant flash, so maybe once every 10th of a second or something like that. All right, so delta t is the same for each, but the feather falls a greater and greater distance during delta t, each delta t, which indicates it's accelerating. If we go over here and we look at this, we'll find that the ratios are in the increasing bit is what you'd expect from a t-square law, so it's the constant acceleration. And then we see that the apple and the feather always stay at the same vertical height. At every flash, they're at the same height, so they must be accelerating at the same rate as they go down. A couple of caveats. This really only works if we can neglect air resistance and other influences. And it really only works over so-called short distances near the surface of the Earth. But since the Earth's radius is 6,400 kilometers, or 6.4 million meters, near can mean something like several kilometers of height. The biggest I've seen on this that this has worked is an evacuated chamber over in Japan, where you can drop it for 400 meters, and the object falls in free fall for most of that time. Under these circumstances, any object falls with a constant acceleration. We generally symbolize the magnitude of this acceleration as g. For objects near the surface of the Earth, it has been established experimentally that g is plus 9.8 meters per second squared. Note that g is defined as a positive constant. Right? It is the number 9.8 meters per second squared. Now, usually we define upward as the positive direction, and things will tend to fall downward, so they will tend to fall downward with a negative acceleration. And so we end up that generally, in the case where we have upward is the positive direction, we have the acceleration of something is minus g. But you really want to keep in mind that g is the positive number 9.8 meters per second square. Some students like to use the idea that the acceleration is minus 9.8 meters per second square, and they'll say the acceleration is g, but those things are contradictory. G is always just a constant. It doesn't have a direction by itself. It's a magnitude. And then we have to attach a direction to it by attaching it to our reference frame. The value of g actually varies a little bit from place to place on the Earth, but we're going to use 9.8 meters per second squared and ignore the variation. Anywhere on Earth, near the surface of the Earth, the acceleration is rounds to 2 digits to being 9.8. It can be, as high as 9.8, something like 2, and as low as 9.76, I think. But in all cases, when you round to only one decimal place, you'll find that it rounds to 9.8. The small variations in g actually allow you to map the density of the Earth, and we'll talk more about that when we get to full-on gravity later in the class. Objects that are moving only under the influence of the Earth's gravity are said to be in free fall. Despite this verbiage, objects in free fall can be moving upward. Yeah, it's a silly choice of words. All right, we weren't very careful here, but things can fall upwards in physics. We usually don't say that. We won't say an object is falling upward. We'll say it's in free fall. All that really matters is that they can be quote-unquote free, not affected by anything but the local gravity. Of course, the Earth doesn't really get a privileged status here. Near other astronomical bodies, objects will be in, quote, free fall, but the magnitude of their acceleration would be different. So on the moon, you'll fall towards the surface of the moon, and you'll have roughly 1/6 the value on the Earth, so 1.6 something. And on Mars, you'll have about 0.4 times the surface gravity of the Earth, so you'll have something like 4 meters per second square. And on Jupiter, you get something at the edge of Jupiter's atmosphere, the acceleration would be something like 25 meters per second squared. So it varies a lot from place to place. It's not a universal constant, but on the Earth, for almost all of human history, it would have been the same number. This is a placeholder for a video that was filmed on the moon, which I like to call the most expensive experiment in the history of introductory physics. And on that, the astronaut drops a hammer and a feather at the same time and shows that they actually land on the moon at the same time, showing that in vacuum things have the same downward acceleration of the same magnitude, although obviously slower on the moon. This is a video linked on the class website if you want to watch it. It's about 1:22, or you could probably search for hammer and feather on moon on YouTube, and you'll see it. It's pretty decent. I mean, it's 1:22 of somebody hamming it up for the cameras, but it's pretty good. All right. A ball is thrown straight upward and then falls back to the same height. A student makes this graph of the velocity of the ball as a function of time. What, if anything, is wrong with the student's graph? If something is wrong, explain the error and how to correct it. If the graph is correct, explain why. This is an error. The ball is thrown straight upward and then falls back downward, so it will come to rest when it reaches the highest point. In other words, if we sort of sketch what's going on here, somebody throws the ball and it goes up and comes back down. At this moment, it's at rest. So the velocity has to cross the t-axis, which it does right there. So that's good. But then for the later moments, it's heading downward. And we have sort of implicitly here said that upward is our plus direction. So heading downward means that it should be negative. This thing should continue onward from the point where it was thrown. And so it looks like this. And this bit is incorrect. It doesn't suddenly start moving upward again. Now you might wonder, but it does get faster. Like it slowed down and it hit and it got faster. So you could equivalently have crossed this out, and they could have written. Actually, let's be careful. Let's actually draw it. We could have said on the original graph that we have the speed versus the time. And in that case, the speed definitely decreases and then increases again. So we could have done it either of those ways, but without one of those, then it's incorrect. The symmetry of free fall. Notice that it takes exactly as long to fall from the maximum height as it took to reach it. So this is some ball or something thrown upward. And remember, it's being thrown up and down, but we just plot its height as a function of time, and we get this nice parabolic curve because it's constant acceleration. And notice that the time it takes to get to the maximum height is exactly the time it takes to reach back to the ground again. In fact, that's true at any time. So if we take here, the time to go from this to the maximum height is the same for it to come back to that height. That's a symmetry of the graph because it says that there's something that's invariant when we change a condition. All right, and this is a useful factoid to put away. The total time of flight is always twice the time to the maximum height. Again, we're saying if we start and end at the same height, which is important, but we usually use that out of the English part of it. And that's a really useful result, as well as being something deep and true. It's nice to know that the time of flight is twice the time to the maximum height. That makes a lot of these problems a little simpler. A less obvious symmetry is the speed on the downward portion is always the same as the speed on that height on the upward portion, only the direction is different. So if we decide to sketch our tangent line, and then we sketch it over here at the same moment, oops, that's not so great, but like that, we can see they have the same slope, just one is upward and one is downward. And again, that's true at any height that you pick. The speed going upward will be equal to the speed going downward. And that's also a useful shortcut in a lot of problems. We see similar symmetries in the velocity and acceleration graphs. So the thing on the left is the velocity graph of the thing thrown upward. It's got an upward velocity, and then it loses upward velocity as the Earth pulls down on it. Eventually it comes to rest at the top of its arc, and then it starts going downward, but with increasing speed. So again, we have something like this. Notice here that we see it's a line, so even at the moment that it's at rest, it has the same acceleration. All right, so we'd say like this acceleration is g, I guess minus g technically, and this acceleration is minus g. And right here, we have the same thing, and so also minus g. AP Committee is really fond of seeing that you know what happens at the top of arcs, because many students want to say that if I throw something and it goes up, then at this point it is at rest, which is true. But they also want to say that at that moment, you know what, let's do it this way. Go up, come down. At the top, it's at rest. Oops. And that's certainly true. But students want to say no acceleration, and that's false. because the acceleration, as we can see from the velocity plot, is constant. It doesn't change even for an instant at the top. If we look at the acceleration plot, of course, it's just a horizontal line. That also has a symmetry. It's a little degenerate, but kind of useful. Notice that from our graph, at 3 seconds, the ball hits the floor again, and it's no longer in free fall, so we can't continue past there. Right? That once we reach this point, it's going to do something as it comes to rest, as it hits the floor or whatever, and it's going to be very complicated, and we're not in free fall, so we can't use the equations.